Hello everybody. Today I'd like to explain algorithmic differentiation in an intuitive way. I've prepared a little example for you. So this is a simple scalar expression that depends on inputs x, y and z. And you could represent this computation in a graph as follows, where this node would mean the multiplication of x and y. Here would be the addition of x and y. Here multiplication of this sub-expression with the z variable and an addition for the last node. What is the goal of this exercise? It's to compute the gradient of the expression v. So the terms you see here are the ones that we're after. So let's start. I'm going to start with writing some sub-expressions that will help us to understand this expression. So I'm introducing an intermediate variable w1 that is nothing more than x times y. Intermediate variable w2, x plus y. 3, that's w2 times z. And finally, our final expression v that you want to compute the gradient of is w1 plus w3. Now this is very concrete with multiplications and additions. Let's write it a bit more abstract by writing it as functions. So in general, we want a binary function here. In this case, binary function of x and y. For the second line in our algorithm, we write f2. It's again a function of x and y, but a different one. Again, we have function. This time it depends on w2 and z. And lastly, we have function f4, which depends on w1 and w3. So let's take the derivative of this guy. Let's see what we learned back in high school and apply the chain rule. First, I'm going to write v in terms of all these functions. Okay, so v is function 4 with argument w1, and w1 is f1. And the second argument of f4 is w3. So that's given by f3, with the first argument being f2. So it's z, close the brackets. So that's the full abstract form of this and what you see depicted in the graph representation here. So how do we compute the derivative of this? Total derivative of v, dv is the partial of f4 with respect to its first argument. And I'm inventing this notation with the p to denote the first argument. So, derivative of f4 with respect to the first times the differential of the first input plus partial of f4 with respect to the second times f3. And now we can go further and expand these as we go. So f1 in itself is given by partial f1 with respect to p1 times dx plus partial of 1 with respect to the second argument times dy. This guy. The total differential of f3 is the partial of f3 with respect to the first times the total differential of the first argument, which is f2, plus partial of f3 to the second argument and dz. So now it's starting to look like this. If we keep doing this, actually there's just one expansion to be done, we will end up with a lot of terms involving either dx, dy or dz. And if we collect the terms correctly, we end up with these unknown expressions that we're after. Okay, so let's take a look at dz in this case. So dz has a multiplication factor, the partial of 3 with respect to the second argument. We can actually see that in the graph. So here you see, and the term I just mentioned is really this guy. And this whole sub-expression is also filled in here. So it's multiplied with partial of f4 with respect to the second argument. So actually what we could do is just write all these partials at each edge and just bubble upwards from the output to the inputs and collecting all the factors that we encountered. So for dz, we will simply have w4 p1 times partial of f3 with respect to p2. That will be here. For x, we can go 2 routes, so it's this plus this. So concretely, we will have a sum of products. First product, this edge times this edge. Second product, this. Okay, so this was the basic route using nothing but the chain rule that we learned in high school. And next next part is how to do this in a structured way with reverse modes of algorithmic differentiation. So in the first block, we've seen how we can use a chain rule to get this gradient. And we can do this, we can interpret this as bubbling upwards in the expression graph. I just spotted a mistake here. We just bubble upwards, going all the possible routes that bring us from the output to the input. Now, going up all possible routes is not really straightforward algorithm to do. So reverse mode algorithmic differentiation is just a structured way to do this. Well, at least that's a way. That's one way to look at it. So what I'm going to do is introduce actually intermediate variables for all the nodes and for all the inputs. And these intermediate variables, I'm going to write with a bar on top of them. That's just convention in our community. So how does it work? We first do a nominal pass, assigning values to all these variables, and then we do a reverse sweep. So the reverse sweep starts at the end, naturally. So this is one expression. It's dependent on W1 and 3, and it's the information of arising from V is going to bubble upwards towards the nodes 1 and 3. So that's why we're going to say W1 bar, which is, as I said, a new intermediate variable that we can use in our algorithm. What we're going to add to this is V bar times the partial of F4 with respect to P1. And we have another update to make, and that is W2 bar plus equals the seed V coming in and the partial of F4 with respect to the second argument. So what does this all mean? I'm doing an update. It means I first have to assign it, and we're actually going to assign all these intermediate bar quantities to 0, except for the very last one. So we have V bar arriving in and bubbling upwards. And we're just going to put V bar equal to 1. Okay, that's what you need to know to interpret this line. So this line translates to this. Second line is this. So this operation involves W2 and Z. So we're going to have an update rule involving W2 bar and Z bar. And we're bubbling up information from the W3 variable. Another mistake. So we have the partial of f3 with respect to p1 and p2. So the v bar has been propagated and w3 has been updated. And this information is used again here to arrive at w2. And we proceed 2 times more, and then all information comes up. So this corresponds to here. Here we have x bar plus equals and y bar plus equals w2 bar partial with respect to 1, partial with respect to argument 2. Right, last one. W1 bar partial of f1 with respect to first argument w bar 1, w1 bar, and the partial with respect to p2. That's really the gist of reverse mode algorithmic differentiation. So you initialize bar quantities to 0, only the output one you put to 1, and then you do a nominal pass and then a reverse pass. And you can see from this description that the side of the algorithm here from the nominal pass is kind of copied for the reverse. So it costs, like the cost to compute this whole gradient is a small multiple of the cost of doing the forward or the nominal recipe. So that's one big advantage of reverse mode algorithmic differentiation. One thing to note is the use of memory. So when I say here we're bubbling upwards, f4 and the partial of f4 with respect to p2, this is actually dependent on these intermediate variables. So that's why we first need to compute these steps, store these in memory, and then later evaluate the partials using this stored data. So that makes algorithmic differentiation or reverse mode memory intensive. There is also a forward mode that has different properties and doesn't use this excessive memory, but reverse mode is much cheaper to do gradients of scalar functions. I mean, you can have 1 million inputs, and just with one reverse sweep, you can get all the gradient for a couple of times the original cost. So that's what I wanted to tell you today.